Hello, welcome. Okay, let's begin with the presentation. Well, the proposal I would like to present consists in the integration and management of three types of renewable energy: renewable solar thermal energy, photovoltaic energy, and aerothermal heat pump. According to low energy demand construction standards, and logically passive house in particular, the higher efficiency of active systems used, together with the production of renewable energy on site, is acquiring greater importance. The aim of this presentation is to introduce a system that integrates and manages three types of renewable energy, as I mentioned at the beginning: aerothermal high-efficiency heat pump, solar thermal energy, and photovoltaic solar energy. This overall system, in addition to these three renewable energies, incorporates an integrated energy management system which seeks to maximize and optimize at all times the use of each of these three types of renewable energy. It also provides a smart grid protocol to prioritize and optimize the photovoltaic energy that's generated. The reduction in energy consumption is a factor that is going to acquire more and more importance in the future, a future which will be characterized by increasing population, which is something that we all know, and also an increase in energy consumption. This is something we can normally read about in the newspapers, so we're familiar with this. Furthermore, all of this within the context of a future in which decarbonization and mass electrification of systems is unquestionable. Therefore, apart from reducing energy demand, of course, obviously one logical objective established as a priority is to lower consumption as much as possible, necessary to satisfy comfort aspects related to heating and cooling and the production of sanitary hot water through the use of renewable energies. Furthermore, if these renewable energies can be produced on site and at the same time we can achieve almost zero energy consumption buildings or homes with positive energy generation, in other words, they generate more energy than they consume, well, I think that we'll be on the right track. And within the context of this future, I believe that heat pumps will probably be a debatable factor, something that we can see every day. Heat pumps, thanks to their versatility and thanks to the efficiency value just achieved, well, perhaps these pumps represent the reference or benchmark system when it comes to meeting these comfort needs and air conditioning requirements, and of course, sanitary hot water requirements as well. In recent years, we have witnessed a revolution in the field of heat pumps thanks to the introduction of new coolants, such as R32, which, thanks to its thermodynamic properties, allow us to achieve not just certain efficiency values that are much superior to those of their predecessors, but also, well, in fact, efficiency values above 5, but also flow temperatures or higher water temperatures simply through the use of refrigeration cycles. This is something very, very relevant, of course, for water production, specifically hot sanitary water production, something that will always require high temperatures, but also in all refurbishment or rehabilitation projects where terminal elements cannot be changed. For example, where we would have to maintain radiators. So in this way, we don't lose efficiency, and we can also adapt these heat pumps to installation demands. Furthermore, thanks to the use of R32, we can lower CO2 emissions. As you know, this coolant has lower atmospheric heating potential than its predecessors, and it also requires less gas charge to operate. So it requires less gas for the compressor to operate, achieving the same power. All of this combined means that the total theoretical heating potential is much lower. So the use of energy contained in outside air, which is basically what an aerothermal heat pump does, is not the only way in which that energy can be used. We mentioned at the beginning that we were going to use 3 types of renewable energy that use the sun as a source of energy: photovoltaic solar energy, aerothermal energy, of course. So in this way, we aim to achieve a system which is not only 100% renewable during most of the year, but which will also reach peaks where production is higher than consumption. In this way, we can transform the installation into a positive renewable energy generator. For me, this slide is the most important in the presentation from a conceptual standpoint. It presents exactly what we're trying to show: an aerothermal heat pump offering high efficiency, R32, 4 kilowatts, in other words, very little power, which will service air conditioning and also sanitary hot water production, or supported or replaced even by thermal solar energy and supplemented by photovoltaic solar energy. This photovoltaic solar energy will cover the consumption of the heat pump, but not only that, it will also cater for other demands that do not necessarily have to be related to indoor climate in the home. And whenever production exceeds consumption, well, that energy surplus, that surplus energy can then be transferred to the grid, which, as you are all aware, is possible thanks to legislative changes in recent times. So there are many factors involved when it comes to choosing the type of backup solar power. For example, the return on investment period, percentage of radiation, and in this case, as an image is worth more than 1,000 words, I wanted to show this picture from a school solar radiation atlas in Spain. And we can see that mean global irradiance in most of the country is exceptional. Therefore, the possibilities for using and taking advantage of solar energy are practically infinite. As I mentioned previously, new generations of aerothermal heat pumps with R32 reach seasonal values that are higher than 5. The system proposed here is a 4 kilowatt heat pump with an integrated hydro kit, a multi-energy kit. What does multi-energy mean? Well, this is a thermal battery. It's a tank and accumulator, 300 or 500 liters, that incorporates different heat exchangers. They are made from corrugated steel with a very large exchange surface. And through these, we can exchange or access energy from that 300 or 500 litre tank. We can access power from the heat pump powered by a photovoltaic energy panel. And also from the solar thermal installation, we can even harness energy through an additional heat exchanger, which can be connected to a heat recovery process. For example, a pan that can recover heat, or for example, from a wood stove in a chimney. So we can accumulate all of that energy in this multi-energy tank or deposit, and then extract that energy for different uses. And in this case that we're presenting here, it will be for heating and also sanitary hot water. The right-hand image shows a section of this type of deposit or tank during operation in cooling, well, logically, accumulated energy is heated up solely with thermal solar energy and will exclusively supply the sanitary hot water. So during the winter period, when there's heating demand, well, this thermal battery will use part of the energy that's been collected in the tank or deposit to preheat the return of installation water, and that will be during part of the year, depending on solar catchment. And heating can also be practically covered with thermal solar energy. In this way, during the months of greatest solar radiation, combining these two types of energy, logically coupled with the high efficiency afforded by the seasonal heat pumps, this will mean that the energy balance is zero, or may even be positive. Positive from the perspective of the installation, from the user standpoint. In the case of surplus photovoltaic production, through smart grid protocol I mentioned at the beginning, the heat pump will automatically increase set point temperature of that energy battery, that accumulator. So the equipment will accumulate energy in those 300 or 500 liters, depending on the model selected, because our aim is to maximize the use of photovoltaic energy. In other words, before transferring to the grid, we can increase the set point temperature and transform captured photovoltaic energy, electricity, into thermal energy. We can transfer that energy, collect it in the thermal battery, and use it for sanitary hot water, of course, or for heating. For quite a long time, we've been talking about these type of energy batteries. On the left, you can see a simple outline of the performance of these type of tanks, 300 or 500 liters, which is warmed, heated more or less depending on production. And production, as we said, will be prioritized thanks to the use of smart software in order to use the renewable energy that's most available at the time. So we can heat the 300 or 500 liters through different heating coils, and through other heating coils, other stainless steel heat exchangers where we can extract the energy. These are semi-instantaneous sanitary hot water production systems, similar to a boiler. Boilers, at the end of the day, are instant production systems. We can only produce sanitary hot water when there's demand, and the same occurs here. What's accumulated is not hot water for consumption, it's not sanitary hot water for consumption, it's energy, and also mains water. So whenever there's demand, whenever somebody opens a tap, it will pass through a heating coil, a very long and large surface area heating coil, and it will be passed continually as it passes through. These are polypropylene deposits or tanks, so there will therefore be no problems of corrosion, and hence there will be no need for protection systems to prevent corrosion. All that's accumulated is energy, and as a result, maintenance is zero. Well, this is a schematic diagram of what I've been describing. In the example, there are 4 thermal solar panels that can operate as pressurized solar panels or dreamback system, transferring the energy to the sanitary hot water tank. There's 2 photovoltaic panels, as you can see in the image, which feed the heat pump, and the heat pump's smart software will decide what to do with the accumulated energy. In other words, it will logically prioritize the consumption of all of the energy that's 100% renewable. thermal and solar photovoltaic energy. You know that aerothermal energy is not 100% renewable. There's a component that is not renewable. First in heating and then in sanitary hot water, we can accumulate that energy in a tank and extract it for sanitary hot water as a priority. And when there's no demand for sanitary hot water, we can pass the return from the heating system of the deposit. We can let steal energy and we can use this for terminal elements. After extracting all of the energy from the tank, the heat pump will be activated, powered by the solar panels, the photovoltaic solar panels in the system. Well, in the example proposed in this system here, we opted for a photovoltaic system with 44 collectors fitted with microinverters. In my opinion, the microinverter system is very good because it transforms each panel into a standalone installation. As you know, more traditional photovoltaic facilities, installations with multi-string, multi-inverters, well, a shadow on a panel will penalize the rest of the row. So with the use of microinverters, each panel is autonomous, it's standalone. Shadow falling on one panel will only affect that individual panel. We selected Cartagena in Murcia as an example, as this was going to be the venue for the conference, or the presence-based conference. So to some extent we wanted to keep Cartagena involved some way. So we have collectors with an efficiency of 19%, pitched 45 degrees south. As you can see, annual photovoltaic production exceeds consumption of a 4 kilowatt heat pump. That's nominal capacity, and with a seasonal performance above 5. Therefore, annual photovoltaic energy is 2,387 kilowatts per hour, which will exceed the consumption of the heat pump. So what can we do with that surplus energy? As I mentioned before, this will be accumulated in that thermal battery, increasing set point temperature, transforming electricity into thermal energy, and surplus energy that we no longer need to use, well, it can be transferred to the grid. The system is complemented by the contribution of thermal solar energy via a series of thermal collectors located in the same place in Cartagena in Murcia, pitched in the same direction. And these collectors will provide energy which is higher than the demand for sanitary hot water calculated for 4 people. So in this way, we can use that surplus energy for heating purposes in the months in which heating is required. Okay, to summarize this presentation, I would highlight a number of points. Integration with control. We can still use different types of renewable energy and get used to seeing different energy sources as allies and not as enemies. There's no reason to choose either aerothermal or solar energy, aerothermal or thermal solar energy, and thermal solar energy and photovoltaic energy. Of course, inside buildings with very low energy demand, and also with on-site energy production. Because at the end of the day, this is what this system is about. And logically, all of this can be controlled and managed using smart software, which will prioritize the operation of one source of energy or another, seeking at all times to optimize on-site resources. Thank you very much for your attention.